Hello, students. I'm Alok Kumar, Senior Faculty at Sri Chaitanya IT Academy, Hyderabad. Yesterday, we had discussed limit. I would like to take off from where I stopped yesterday, and we will be covering more challenging problems. So let me now share the screen and start the lesson for today. Okay, so yesterday we had revised the concept of limit, and I had done some problems which were some medium level and some were just JE advanced level also. Today I would be doing more challenging problems, so please pay special attention to it. So let me write the problem first. A couple of problems, they will be on recurrence relation. So let me write a problem. So number one that I want to discuss is like this. There is a sequence of real numbers defined by a1 equals 1, an equals n times sorry about that, an equals so okay, come back, welcome back. An equal to n times n equals n times I have got some trouble in applying the application. So let me just write n is n times n minus 1 and get the मैं तो यहीं पे मैं तो लाइव में गो लाइव मैं गो लाइव करके मेरा वर्ड से नहीं हो रहा है मेरा हाँ हाँ मैं भी मैं अपने को देख पा रहा हूँ आई एम तो कैमरा इज ऑन Sorry about that. There was some technical glitches. Okay, so I was just starting. So I have got a1 equals 1, an equals n times 1 plus an minus 1, n greater than or equal to 2, and then we have to find the limit, that limit n tend to infinity of 1 plus 1 over a1, 1 plus 1 over a2, till 1 plus 1 over an. So this sequence is defined by a recurrence relation, and one has to find the limit of it. So this is will be my number 1. So in such situations, the first thing that you must do is to play around with this equation in different ways. For example, I can write an equal to n times 1 plus an minus 1 as 1 plus an minus 1 upon an equals 1 over n. This is one of my relations that I will use repeatedly. So let's apply it. So let me call this P as 1 plus 1 over a1 times 1 plus 1 over a2 and 1 plus 1 over an. And I simplify a bit. So 1 plus a1 times 1 plus a2 times 1 plus an whole upon, I write a2 first, then a3, all the way till an, and the left out a1 happens to be here. So using this relation 1 plus an minus 1 upon an is 1 over n, I would like to write my p in some special ways. So it's like this. Now, in view of the relation, the boxed one, and I just checked it also, 1 plus an minus 1 upon n is 1 over n. So 1 plus a1 over a2, this bracket, this one, this equals 1 over 2. Then the next one is 1 over 3, all the way to 1 over 1 plus an upon an. So that will become n plus 1. And then this is 1 over a1, so that is given to be 1. So we will get here equal to equal to 1 upon 1 upon n plus 1 factorial. And one more thing will come, that is 1 plus an, and so I can write this as an plus 1 upon n plus 1 factorial. So now I have to find the limit of an plus 1 upon n plus 1 factorial, limit n tend to infinity. This number also can be done in a different way. That is, again, go back to the definition. An is n times 1 plus an minus 1. So this an is n times 1 plus an minus 1. I can divide the whole thing by n factorial. So an over n factorial is 1 upon n minus 1 factorial, and 1 plus, or rather I can combine them together and I can just write that this is n plus n an minus 1 over n factorial, giving me 1 upon n minus 1 factorial, and plus an minus 1 upon n minus 1 factorial. These two are same expressions, just n changed to n minus 1. So it makes good strategy to bring them on one side, and so write like this equals 1 upon n minus 1 factorial. This relation, I can write from n minus 1 onwards. So an minus 1 upon n minus 1 factorial minus an minus 2 upon n minus 2 factorial is 1 upon an minus 2 factorial, all the way to a2 upon 2 factorial minus a1 upon 1 factorial is 1 upon 1 factorial. I can add them up. These all columns, when added, these things will cancel in pairs. And so you are left with, we started with an upon n factorial. So you are left with an over n factorial minus a1 upon 1 factorial. And then the top number was 1 upon n minus 1 factorial. So you will get 1 upon n minus 1 factorial plus 1 upon n minus 2 factorial all the way to 1 by 1 factorial. So I can write an upon n factorial is 1 by 1 factorial plus 1 by 1 factorial. This comes twice because you are given a1 equals 1, 1 by factorial 2 till all the way. And we want to find now limit n tend to infinity an plus 1 upon n factorial plus 1. That is same as limit of n tend to infinity an over n factorial, an over n factorial. The reason being that when n tend to infinity, so does n plus 1. That also tends to infinity. So this step is justified. And then by definition, we know that E equal to limit of n tend to infinity 1 plus 1 by factorial 1, 1 by factorial 2, all the way. And so this expression, that the limit, this equals 1. This equals E. So that brings to end our first question. Let me insert some pages in. So let me review what we did just now. That so we have done this one, that the relation was given to be a1 equal to 1, a1 equal to 1. So let me highlight and show you the important steps. So it was a1 equal to 1, then an is n factorial. So this was the given recurrence relation. We played with this recurrence relation here. N is n times 1 plus n minus 1, and rewrote it this way. And we used them repeatedly to arrive at the expression in the last, that an plus 1 by n factorial. So whatever is left is that we want to find this limit. Again, we have used the same recurrence relation in a different way by dividing n factorial. And then it's sort of telescope from here to here. It is telescopic. And when we telescope the sum, we end up with the expression for an over n factorial, this step. And then by definition, we know that E is the limit of that. And that was our answer. Here, this step was there, that we have to write n factorial. And I told you that these two are equal. And so you will get the answer as E, because E happens to be, as I wrote somewhere, that E happens to be limit of n tend to infinity, by definition 1 plus 1 over 1 factorial. So many ways to define E. This is also one of the ways. So this goes till here. And then this answer, of course, becomes E. So my boxed answer, that answer is E. Let us go along in the same direction and do some more problems. So let me change the color a bit. So if I take the other problem, number 2, it's also defined recursively a sequence. So that sequence is x naught is 2 times cos of pi over 6, and xn is defined to be xn and xn is defined to be a square root of 2 plus xn minus 1 n greater than equal to 1. The lower limit is very important because that tells you that recursion starts at n equal to 1. This is of fundamental importance. And our job is to find, the questions ask you to determine or find limit as n tend to infinity of the expression to the power n plus 1 times square root of 2 minus xn. This limit is to be found. Now let's again do some substitution. Because x naught is given to be 2 cos pi by 6 for a reason, thus 2 appears. Let me start by writing that x naught is twice cos theta naught, 2 times cos theta naught. Theta naught happens to be pi over 6 for our example. Now x1, if I use recurrence to find x1 is root of 2 plus x naught using this recurrence. So that gives me square root of 2 plus 2 times cos of theta naught. I can take 2 common over there, and 1 plus cos of theta naught. That equals 2 times 2 cos squared theta naught over 2. You remember 1 plus cos t is 2 cos squared t over 2. So use that result. So we'll get this one, and that happens to be twice cos theta naught over 2. That is my x1. If I have to go x2 one more step, x2 by recursion is 2 plus x1. That is 2 plus 2 cos theta naught over 2. This is exactly in the same way, 2 times 1 plus cos of theta naught over 2, and 2 times 2 cos squared of theta naught over 4. This theta naught becomes theta naught over 2. Exactly in the same way, this theta naught by 2 becomes theta naught over 4. And we get 2 times cos of theta naught over 4. So you notice that we started with theta naught, then we got theta naught over 2, then theta naught over 4. It's familiar pattern, it's GP. That expression tells you. So when you go to last step xn, the xn that I want, that xn should be 2 times cos of theta naught over 2 to the power n. Be careful over here. Some people make the mistake n minus 1, or some count more n plus 1. Neither of them is correct. A simple check tells you, you write 4 as 2 square, 2 as 2 1, and so you match. This 2 and this 2 are matching. Similarly, this 1 and this 1, they do match. So in fact, we have got x of n. X of n is 2 times cos of theta naught over 2 to the power n. That is your xn. Now we are all set for our final answer. So we wanted to find limit as n tend to infinity of the expression 2 to the power n plus 1 times root of 2 minus xn. That equals limit of n tend to infinity 2 to the power n plus 1. We already know xn. So this is 2 minus 2 cos theta naught over 2 to the power n. And this expression becomes limit of n tend to infinity 2 to the power n plus 1 and 2 times 1 minus cos of theta naught over 2 to the power n. Now we use 1 minus cos t is 2 sine square t over 2. That will give you limit of n tend to infinity 2 to the power n plus 1 times 2 into 2. And this number becomes further sine squared theta naught over 2 to the power n plus 1. And so we get limit as n tend to infinity of 2 to the power n plus 1 and times 2 sine of theta naught over 2 to the power n plus 1. It's a really long problem, but worth it. Now the last steps are just to use the famous result that limit of t tend to 0 sine of t over t equals 1. One of the first limits that you learn in your class. Using this, we can write this as limit n tend to infinity 2 to the power n plus 2. So this will be 2 to the power n plus 2. So I don't disturb this. I will just write sine of theta naught over 2 to the power n plus 1 whole upon, it's like adjusting theta naught over 2 to the power n plus 1. So we are basically getting sine t over t. This is my t. Our t for this example is theta naught over 2 to the power n plus 1. And as n tends to infinity, t tends to 0. So we are good. Now, let me adjust these things now. This is here, you will get 2 and then theta naught because theta naught is not here. And 2 to the power n plus 1 comes down. Now we take limit. This whole limit is 1. So we'll write limit n tend to infinity sine of theta naught over 2 to the power n plus 1 upon theta naught over 2 to the power n plus 1 times limit n tend to infinity to theta naught. So we have done under certain circumstances that limit of products equals product of limits. The first limit equals 1. The second has no n in it. It's just 2 theta naught. And now we get back to our theta naught. Our theta naught was pi over 6. And so 2 times pi over 6. That answer becomes now pi over 3. So that's my final answer, pi over 3. Let's rerun it. That it's a long one. So we are given this one. So we are given this recurrence relation that x naught initial value, it is called sometimes seed value. It is sometimes called initial value, or so they are called sometimes initial value, or they are called seed value. So x naught happens to be seed value, and then you are given xn is square root of 2 plus xn minus 1, n is equal to or more than 1, so n greater than or equal to 1, and then you want to find certain limit. So the whole idea was how xn behaves and whether we can determine xn in closed form. That we did. We started with x naught is 2 cos theta naught. Then we found pattern for x1. x1 was 2 cos theta naught over 2. And then x2 was 2 cos theta over 4. That was enough to conclude that xn is 2 cos theta naught over 2 to the power n, because these all theta naught are in GP. The next step was to calculate the limit. So we simplified this expression, of which I had to find the limit. And then in the last step, we got this as our expression. And this limit, we have just using sine t over t equal to 1. It's minor adjustments. And your answer comes out to be 2 theta naught. And so that's our answer. Okay, so now let me go to some next question. So I will take up this one now. This again recurrence, but it looks more terrifying. 1 over square root of 1 by 2 times square root of half plus half times square root of half too many 2's times the third term is square root of half plus half times square root of half plus half times square root of half, and so on to n terms. So you want to find the limit of this huge expression as n tend to infinity, because n will come here somewhere. So it is to n terms. Now, this does not look like recurrence because it is not defined explicitly, but we can define. So I'll define like this. I'll take a naught is a square root of 1 over 2. That is your initial value. And then I will define an plus 1 is square root of half plus half an. N greater than equal to 0 because a naught I know. So there is no harm in starting n at 0. I know the seed value a naught. If you look at closely, then our expression, the huge one, that transforms to limit as n tend to infinity of 1 over the first term is a naught, the second term is a1, you got it right, because a1 is half plus half a naught, the third term is a2, and so on. The nth term will be an minus 1. Don't make the mistake of an. We want nth term. This is first term, corresponds to 0. Second, this is first, this is second, and so this is nth. So first term corresponds to 0, second to a1, third to a2, and so on. So we want to find this limit a naught, a1, an minus 1. Inspired by the last example and looking at the form, we go for trigonometric substitution. So we write a naught is cos of theta naught, and this theta naught I can take to be pi over 4 because cos pi over 4 is 1 over root 2. So a naught is defined like this, a naught, and the recurrence an plus 1 will do the job now. So I can write an plus 1 is square root of half plus half an. So put n equal to 0. You should get a1 is, using this one, we'll get a1 is square root of half plus half a naught. So half plus half a naught, that is cos theta naught. So we'll get square root of half 1 plus cos theta naught, and so square root of half times 2 cos square theta naught by 2. And so we get a1 is cos of theta naught over 2. We again used 1 plus cos t equals to cos square of t over 2. So a1 is cos theta naught by 2. If you go to a2, one more step, a2 is square root of half plus half a1. So we write half plus half times a1, that is cos of theta naught over 2. I can take half common. This is 1 plus cos of theta naught over 2. This number becomes root of by 2 times cos square of theta naught over 4. Each time this angle is halved. So it started with theta naught, then theta naught over 2, then theta naught over 4, and so on. So I should get here cos of theta naught over 4, this a2, all the way. So an I will get as cos of theta naught over 2 to the power n. But we have to stop at an minus 1. So an minus 1 is cos of theta naught over 2 to the power n minus 1. We can match from 2 corresponds to 4, and 1 corresponds to 2, 1 corresponds to 2, and so the powers of 2 are like this, and we get an minus 1. A still other way to look at the same thing is that I could have written an plus 1 is half plus half an, and I could have taken an is cos of theta n, then theta n will again give you the same thing, theta n over 2 to the power n. So let's now rewrite what we got using this thing. So this was the problem, that we have to calculate limit of 1 over this one, 1 over a naught, a1, a2, this one. So we go back, and then again we go forward now. So we'll get limit of this. We want now limit of n tend to infinity 1 upon cos of theta naught over 2, cos of theta naught over 4, and all the way cos of theta naught over 2 to the power n minus 1. Please calculate correctly, because that is important in exam. Now, to play with this, we have got one expression. We know that, I write here, we know that cos of alpha, cos of 2 alpha times cos of 2 to the power n minus 1 alpha. So this has got n terms, first term, second term, first term, second term, and this is nth term. So these n terms, so that happens to be sine of 2 to the power n alpha whole upon 2 to the power n times sine of alpha, when these things are all defined. So I would explain like this, that we had got cos of 2 to the power n minus 1 alpha was the last, this was the last argument. So you are just multiplying this argument by last argument multiplied by 2. That gives you 2 to the power n alpha. So that's here, 2 to the power n alpha. This is alpha, the first term, alpha. This alpha is alpha. And 2 to the power n comes because number of terms is n, and so 2 to the power n should come. Apply same formula, but read it this way. So I'll write cos of theta naught over 2 to the power n minus 1, cos of theta naught over 2 to the power n minus 2, and all the way to cos of theta naught. This product has n terms. So same situation, I can think of this as alpha equals theta naught over 2 to the power n minus 1. And this will become simply that, using the same result, we can rewrite this as 1 upon, we will do later. So let me just erase this. Yeah. So we will write this as cos theta naught in this way. So that becomes 2 to the power n times sine of 2 theta naught, and whole up 2 to the power n should go down. So this is sine 2 theta naught over 2 to the power n times sine of theta naught over 2 to the power n minus 1. That's huge expression. This equals this one. We have to invert it and find the limit. So your limit should be now limit of n tend to infinity, and then 2 to the power n times sine of theta naught over 2 to the power n minus 1 whole upon sine 2 theta naught. This I can write as, this 2 theta naught is not a problem, so I will just take it out because n does not depend on it. And limit n tend to infinity This should be written as sine of theta naught over 2 to the power n minus 1. That is your sine t, which tends to 0, and upon theta naught over 2 to the power n minus 1. And this theta naught is extra, so I can write theta naught, and we have got a 2 over here because this was 2 to the power n. So now our answer comes that it is 1 over sine of 2 theta naught times this limit is 1, and this is 2 theta naught. So our answer becomes 2 theta naught over sine of 2 theta naught. Now let me recollect what theta naught was. So theta naught was pi over 4, if you remember. So theta naught was pi over 4 because a naught was square root of 1 over 2. That was cos of theta naught. So that is pi over 4. So 2 times pi over 4, and upon sine 2 theta, sine pi over 2, that is 1. So this is pi over 2 upon 1. So our final answer becomes pi over 2. So today I have taken some longer problems because by nature they are the most tricky problems that may appear on JEE Advanced. And so it's good to have a practice on it. So let me just review it quickly using highlighter to show you the relevant points. So that was the recursion given. In fact, we derived this recursion. The given problem was 1 over root 2, which suggested that there could be some recursion at work. So guided by this and motivated by cos theta, we set up this system a naught, then an plus 1, and all those numbers. So this was the step that we got. A naught is cos of theta naught. Then next was an plus 1 and an connection. And then we found a2. A2 happened to be cos of theta over 4, theta naught over 4, a2. A1 was cos theta naught over 2. And so final an comes out to be cos theta naught over 2 to the power n. But I need only an minus 1. So I'll use this one. An minus 1 equals cos of theta naught over 2 to the power n minus 1. And then I set up the limit. That was limit n to infinity 1 over cos theta naught by 2, and all the way to cos of theta naught upon 2 to the power n minus 1. And we have got a result: cos alpha times cos 2 alpha times cos of 2 to the power n minus 1 alpha equals sine of 2 to the power n alpha upon 2 to the power n times sine alpha. We use this result here backwards, starting from this end, and we got this result: sine of 2 theta naught upon 2 to the power n times sine of theta naught upon 2 to the power minus 1. And then we took the limit of this expression by again using sine of t, again using sine of t over t, limit t tend to 0 equal to 1. And ultimately we got our answer as pi over 2. So that's our final conclusion. Let us take up the next problem. It's again a recursion. So let me change the color in a star. So this is other problem that we're taking. And this time you have got, this is given that this a1, a2 till an, they all are positive real numbers. So a1, a2, an is a sequence of positive real numbers. And the recursion is this time given in the beginning. So an plus 1 is an plus square root of 1 plus an square, n greater than or equal to 0, and a naught equals 0. So this seed value is defined, or initial value, and recursion starts from 0 onwards. That means that I can plug in n equal to 0, I can get a1. Then I can plug it n equal to 1, I can get a2, and so on. And your job is to find out limit of n tend to infinity an over 2 to the power n minus 1. Here the problem ends, and we'll start the solution now. So Let's have a look at the problem again. That a1, a2, an be a sequence of positive real numbers defined by an plus 1 equals an plus a square root of 1 plus an squared, n greater than or equal to 0, and n not equals 0 is the seed value. And one has to find limit as n tend to infinity or limit as n approaches infinity of the expression an over 2 to the power n minus 1. Now, the first question, what does this expression reminds you of? If you see somewhere 1 plus alpha squared, then Trigo tells you something. In fact, people would often answer alpha is tan theta. That comes to their mind. But then let me change and let me write cot. After all, they're same, because 1 plus tan squared theta also simplifies. If things are positive, this will be sec theta. If sec theta is positive, and this will give you cosec theta. But I would prefer this for the reason that will obvious when I work on the problem. So let me make the substitution inspired by the term root 1 plus an squared in the definition of an plus 1. I will make the substitution an is cot of theta n, and let's take all theta n belongs to 0 open to pi by 2 closed. In fact, a naught is given to be 0. So if I find my theta naught corresponding to this, I'll get theta naught is pi over 2, which is all right, because cos pi by 2 is 0 and sin pi by 2 is 1. So cot theta naught is 0. So we are getting cot theta naught. N is cot theta n. Now n plus 1 is an plus root of square root of 1 plus n squared. If I use this n definition, I can write cot of theta n plus root of 1 plus cot square theta n. I'll get cot theta n plus, I should get modulus here, root x square is modulus of x, very important, but x is non-negative, and so it's just x. So this is cosec square theta naught, and so I got cosec theta n. Now I can simplify this a bit. Cos theta n over sine theta n plus 1 over sine of theta n, which gives 1 plus cos of theta n over sine of theta n. Using 1 plus cos t is 2 cos square t over 2. I can write 2 cos square theta n over 2 and whole upon sine t we can write as 2 sine t by 2. So 2 sine theta n by 2 and cos of theta n over 2. And that simplifies a bit, and that gives you cot of theta n over 2. So you started with cot of theta n and you got cot of theta n over 2. Means you started with an is cot of theta n, and an plus 1 comes out to be cot of theta n over 2. Amazing. It's like again GP, the theme we have dealt with in this lecture throughout. So had I started with a naught is cot of theta naught, my a1 will become cot of this theta naught over 2, because at each step the angle is halved. If you pass from an to an plus 1, your theta n changes to theta n over 2. So you are dividing the angle by 2. So a naught is cot theta naught. A1 equals cot of theta naught over 2. When you come to a2, it is cot of theta naught over 4, or write suggestively theta naught over 2 squared. And so one more step, a3 is cot of theta naught over 8 corresponding to 2 cube. And so if I want an, because I have to find the limit for an. So an happens to be cot of theta naught over 2 to the power n. That happens to be my an. It perfectly matches. As I told you before also, be careful about exponent. It's 2n or 2n minus 1 or 2 to the power n plus 1. Chances are sometime you will may write incorrect things like this and this. So please guard yourself against such possible mistakes that will cost you heavily in exam. So an is this one, or an happens to be this. Once I get an, it is called closed form expression. It is called closed form expression, means that your an was defined by way of some recursive sequence, but you have found an in closed form, means you can keep putting the values, you will get a1, a0, a1, all you can get. So let's use this form now. Now you have to find the limit of limit n tend to infinity an over 2 to the power n minus 1. The main job is done. So limit n tend to infinity, an is cot of theta naught over 2 to the power n upon 2 to the power n minus 1. I want to change cot to tan, and so I'll write limit of things go down. So I get to the power n minus 1 times tan of theta naught over 2 to the power n. And then I can adjust the terms because I again know limit of t tends to 0, just like sine tan of t over t, that also equals 1. If I use this, then I'll get this as limit n tend to infinity 1 over now tan of theta naught upon 2 to the power n whole upon theta naught upon 2 to the power n. That takes care of tan t by tan t, and times this is extra, so we should get here this is theta naught and over 2, because we only had n minus 1 and we put n here, so we should get 2 here. Now we are ready, so we can write this as 1 upon theta naught over 2 and times 1, because limit is 1 of the last one and theta naught is independent, so 2 over theta naught, and theta naught is pi over 2, so 2 over pi over 2, so that answer equals now 4 over pi. So that's my answer, pi of 4 over pi. Let me review it. What we have done is, first we have started with a1, a2, an positive real numbers given. So we made the substitution 1 plus alpha squared. If you look, tan theta and cot theta both come to our mind, but I am using here cot theta. So this was our step, that an is cot theta n, that was the substitution, inspired by 1 plus an squared, occurrence of that peculiar term which often arises in trigonometry. And so we got an plus 1. This recursion an plus 1 is an plus a square root of 1 plus an squared, simplifies a bit, and we are getting cot of theta n plus root of this one, ultimately cot theta n plus cosec theta n, and this also simplifies much, and we are getting a very simple expression of this one. Means we got an is cot of an plus 1 is cot of theta n over 2. That means that an and an plus 1, so if you pass from n to n plus 1, then theta n goes from theta n to theta n over 2, means it is halved at each stage. So let's start with a naught. So if a naught equals cot theta naught, then a1 you should get cot of theta naught over 2, a2 we should get cot of theta naught upon 4, and a3 we should get cot of theta naught upon 8, and so on. So we can write our answer as this expression for an is cot of theta naught over 2 to the power n and of course greater than equal to 0 because that was the given thing. Now in closed form expression, always it is not possible, but here it was possible that given a recurrence relation, so here it was possible, a small remark, here it was possible that given a recursion, given a recursion given a recursion, one is able to find what is called the formula for it, or technically closed form expression. Using this one, I determined what an exactly was. So I got this an. Once I got an, after an, my job was simple, because once I get an, then this was my question. The problem asked you to find limit of n tend to infinity an over 2 to the power n minus 1. N minus 1 is on top, and where an is the sequence defined by given relation. Because we know an now, we have determined an, so we'll just put this an, and so this was my an, and upon 2 to the power n minus 1. And now, because cot appears, I can change this to tan, so cot of t is 1 over tan t, and we know that limit of t tend to 0, tan t by t equal to 1. So that means that we just have to now adjust these terms. So the argument of tan was theta naught upon 2 to the power n, that is called sometime argument. So argument of tan function, this number was theta naught over 2 to the power n, and so this is the argument t, so we want a t here, so that they together can give you 1. So tan t over t equal to 1, and so here I adjusted that. I got 1 over theta naught over 2 n times tan of theta naught over 2 to the power n whole upon theta naught over 2 to the power n. That happens to be 1 upon theta naught upon 2 times 1. This 1 comes because this limit became 1 over 1, that is still 1. And so theta naught is one important remark was that theta naught is independent. It is independent of n. So when you take out limit, this is just pulled out. So this becomes 1 over theta naught by 2. And so it becomes 2 over theta naught. So 2 over pi by 2. That gives you 4 over pi. So my final answer of this question becomes 4 over pi. So what you have observed is that in all of these things, either recursion, this is the conclusion, either recursion was explicitly defined means it was just given, for example in this one, or recursion was implicit, means there was no hint of recursion, no trace of recursion, but you just thought that okay, there is some number like square root of half, and a square root of half plus half times square root of half, and then third term was much more huge. This was half plus half times square root of half plus half times square root of half. So this has got 1 2, this has got 3 2's, this has got 1 2 3 4 5 2's. So this is number of 2's is 1, and then 3, and then 5, and it keeps on increasing. So we were made to think that maybe it's a job for recursion, because so we thought of, so it was implicit, and we found this one. The other results were just explicitly given. And one more thing was there, even if defined explicitly, there were two categories. One was that I found closed form, other without closed form. We are able to find limit. In the first example, that was E, that the first started with, and closed form was the last example that we got 4 over pi as the answer. So these two are different things. So in a way, It is always good to spot the recursion. If it is implicit, your solution will be shorter and crisp. And if it is already given recursion, then think of two ways. If you can find closed form, do find it. If you can't find, then look for a way such that using the recursion, you can not find the closed form, but still you can find the limit that is being asked. So that should be okay. So we'll again connect tomorrow. So tomorrow I will be doing limit part 3. In that we will be discussing some more challenging stuff. So till then, have a good day.